All right, greetings, Saintsmen. We are live with lesson 2.6, proving relationships. First thing we're going to talk about, we had this has come up in class, and it's regarding one of the. Let me move this. I got to figure out how to make this thing get out of the way here. Nonetheless, you guys have this 2.6, proving geometric relationships. Um, One of the concepts that we had discussed in class was when the idea of starting a car, right? We don't have to relive the entire explanation of the combustion engine every single time that we're going to start a car. Instead, you just start a car, turn the key, start a car. So one of those things that we're going to use is remember we have the definitions, properties, and postulates, but there was a fourth thing that we could put in the right hand column to justify our reasoning. And again, we don't want to have a crazy long conspiracy theory sounding reason. We actually wanted to have true, succinct, and well cited and truncated reasons. Not truncated, but just to the point reasons. So one of those things that we talked about were theorems, which is a statement that can be and has been proven. So theorems are something, for example, we have one from class. One of the ones that we did was is the congruent supplements theorem. And we'll cite that guy. It's in lesson 2.5. Real quick, just to discuss something. You guys are going to see in the assignment in class, it's going to ask for a flowchart proof. Never do this. We'll always do a two-column proof. And the reason why we're saying that the flowchart proof or any other type of proof, it's flowchart proof, informal proof. There's a lot of ways that they put this down. Um, you don't need to ever do this like that way. That way. We'll always uniformly do the two-column proof. The reason why I'll even assign those questions is because I actually like the question itself, just if and the proof itself, but if it were done in the form of a two-column proof, like the actual concept. So again, show you guys something kind of in all of this is back in 2.5, you guys remember this thing right here where we showed, we had angle 1 and 3, right? We're both, or 1 and 2 are both supplementary to 3. And then when we did this, it showed that when two angles were supplementary to the same angle, they were congruent. So that right there is our theorem, right? So this is where we're going to see lesson 2.5. And we have within our vocabulary the supplement angle proof. That was the first one. That was the first thing that we did. And this was our proof. And our theorem here was that angles supplementary to the same angle are congruent. And this has a name. This guy's name is the congruent. And we talked about this in class too. X, here we go. Congruent supplements theorem. And you guys, of course, can just write congruent supplements, just like that, okay? And that is satisfactory for me. Next, let's remember that we have vertical angles being congruent. Okay, so let's take a look at the following diagram. So we have angles 1, 2, 3, and 4. And here's what you guys are going to tell me. Ooh, that's the wildest looking number 4. Here we go. I'm also going to give you that the measure of angle 3 is equal to 128 degrees. And what you're going to have to find here is find the measure of angles 1, 2, and 4. Okay? So it's a pretty straightforward problem from a problem solving standpoint. For the first one, so we have 3 and we want to find the measure of angle 1. Now, you have to give a justification. You can't just decide something is because it looks like it. It's terrible, terrible, terrible reasoning. Excuse me. Just have something I need to manage in our chat here. Okay. Measure of angle 1 is going to be equal to the measure of angle 3, which is 128 degrees. And this is because these are vertical angles, right? This relationship. They are the two non-adjacent angles, which we know that are formed off of two intersecting lines. And these have a relationship of congruence. So we know they're the same. Now, the measure of angle 2, we know these are going to be supplementary, and the reason why, right, 1 and 2 is because these guys are a linear pair. And I'm sorry, 2 and 3, or even 1 and 3, right? It doesn't matter. We already solved for 1, so we can say that these guys are a linear pair, therefore they're supplementary. So this guy's going to be 52 degrees, right? We're going to back it out from 180. So we have to give our justification, which is that this is a linear pair. Therefore, these are supplementary. All right. Next, the measure of angle 4 is going to be equal to 52 degrees. Well, why? Well, let's take a look here. I mean, we could again say, oh yeah, these guys were supplementary or these guys are supplementary, but very simply put, because we found angle 2, right? And we know it's 52, these guys are also have a vertical angle relationship. So we're going to say these guys are vertical to angle 2, okay? Back here, measure of angle 1 was vertical to angle 3, which is why we knew that that guy worked, okay? Next, let's do another one of these. And there's a critical part in this next one where you guys are going to see, again, where we're going to have this relationship where I have these two that are written here being 101 and 4x minus 3. And you guys can see what the relationship is right away as we're going to solve for x as our problem. But we see this relationship. Ooh, goodness gracious. There we go. We see this relationship, which we know are vertical angles and are going to be congruent. So what we can do is we can set up 4x minus 3 being equal to 101. But here's the critical step. You guys need to justify why we set this up the way that it is. And this is what we have. Because I know you guys can do this algebra, this problem part, but we need to make sure that you cite the vertical angles. So once we do that, now we can just operate. So if you start operating on this thing before that, you will not get full credit. Make sure you take this step, okay? So plus 3 to both sides, okay? So 4x is equal to 104. Then I'm going to divide by 4 on both sides. So x is going to be equal to 26. Okay, last but not least, let's do a proof. I'm going to give you guys a diagram. We'll operate. There's going to be a bunch of points on this. So we have A and E. It's my line segment. And then right here, I have points. Oops, yikes. This is not C. This is B. This one in the middle is C. And this one right here is D. Okay? And here's what we're given. We are given that AB is congruent to DE. And we're also that BC is congruent to CD. And we need to prove that we have AC congruent to CE. Now, guys, we did these in class algebraically. Remember, this has to be our last step. When this is our last step, we are done and we've accomplished our proof. So we now need to create our two-column proof. So let's create our two columns. The left one, of course, being called statements, and the right one being called reasons. Remember, we always have a way we can get started. We can actually set up our two-column proof. Moreover, we can actually just recopy
this first statement, which we're going to have that is AB is congruent to DE, and that BC is congruent to CD. And the reason why, we can just repeat this given step. Okay, this is the statement we can make because it's given. Now, all this stuff that we're going to write on this right-hand side, remember the justifications have to be definitions, properties, postulates, and theorems. So, before I move on, and I think this is a really important part, the dialectic that we're going to engage in with each other, I think it's really important when you guys do these problems at first that you're going to talk to each other, right? And really flesh this out. One of the things I'm going to encourage you guys to do, start to mark it, okay? So we have AB congruent to DE, all right? And then BC is congruent to CD, all right? And now let's talk this thing through. Now, remember, I start with, for example, AB and DE. And for both segments, I could add on one of the other segments here, either BC or CD, as long as I do it to both sides. That's going to be our critical part. Because what I really need to show, because what I need to show is that this entire segment right here, AB and BC, which is AC, and CD and DE, which is CE, is going to be equal to each other, AC and CE. But we can already see the combination of these two, right? The one tick mark and two tick marks, and one tick mark and two tick marks is the same. But we don't want to sound crazy. I can't just say that. I can't say, oh, the one and the two tick marks, right? And sound kind of crazy. I need to actually give real justifications. Okay. Um, so let's do this. Remember we did in class. AB. If I add BC and BC to both, could I do that? Can I just add 5 to both sides? Theoretically speaking. Sure, I can just add whatever I want to both sides, as long as I do it to both sides. So this is just addition. And here's why I'm going to do it. Let's get creative. We did something similar with angles in the last class. What I could do is now, because I have, right, BC and CD being the same, couldn't I do this? Could I just say that AB plus BC, right, is the same thing as DE, but remember what I did here, DE, and I had BC added in. Could I just do a direct replacement here for BC and make this CD? And this guy would be, sorry guys, I'm having a lot of issues with my hand touching the screen here. There we go. This right here, BC and CD, this replacement, it's the same as this. So with the replacement, we don't say replacement. Our term that we use is called substitution. That's the property that we can cite. We just did a direct swap. Now, AB plus BC, back at the top. Segment plus segment is the big segment, AC. Also, DE plus CD. Segment plus segment was the big segment. So let's actually cite each of those. AB plus BC was equal to the big segment AC, as well as DE plus CD was equal to the big segment CE. This is segment plus segment where there's a shared point to create a bigger segment, and this is segment addition. So, we're ready, guys. We can actually say, because we want AC is equal to C, congruent to CE. And I don't care about that definition of congruence. We can use equality and congruence interchangeably in this course. So I have AB plus BC, AB plus BC, right? Right? And they are going to be equal to AC, because I have these three things each used twice, right? This guy used, right? DE plus BC, but I have DE plus CD, and then DE plus CD, but it's equal to CE. So I can say that AC is congruent to CE, because AB plus BC is DE plus CD, and AB plus BC is AC. DE plus CD is CE. This is the transitive property. It's my little syllogism that I have here. All right, there we go. I'll see you guys in class. If you have any questions, please reach out. I'll answer some questions in the chat.